All right, so I made some last-minute changes. So it's always a bad idea when you do that, but we'll see. Okay, so post-exam, which we'll be grading this week, should get it back Friday at the latest, maybe Wednesday, but no promises there. We were talking about ideal gas mixtures. So we had already introduced the nomenclature that we were going to use, where we had the overbar as something that was in the mixture. The underbar was either the pure species. So let's just do a really quick Q&A. This is called the what? Partial molar property. We know it's for an individual species because we have the subscript, we have the overbar, meaning that's how it behaves in the mixture. The reason why we particularly care about this is because the partial molar Gibbs free energy is constant across all of the phases, and this is what we're going to use to gain access to multi-component, multi-phase equilibrium. Likewise, the partial molar fugacity, which is defined on that handout that I provided. It's also posted on Canvas as, I think it's called Fugacity something, as one of the files. Right, so this is going to be the same gateway that we use to do phase equilibrium for single component systems, but now we're going to do it for multi-component. Now, what does this symbol represent? It's the total property, either of a pure component or it could be of a mixture. Typically, when we're talking about mixtures, we'll give ourselves a little subscript reminder. So if we have a system like this, we know it's only going to be a function of temperature and pressure because it's the pure species molar property. If we don't have an underbar, it could be just because of sloppy notation, or it could also be that we're dealing with something in a mixture, which means it's going to be a function of temperature, pressure, and composition. So oftentimes I'll write this X with a bar under it, just saying, I think that's the same notation the textbook uses, basically saying, yeah, it changes as you change anything, right? Any of the mole fractions change, the whole system property changes. Nothing stays the same. So what we talked about was that for ideal gas mixtures, we had a couple of relatively simple relationships. We had the partial molar internal energy for an ideal gas mixture. Now recall this is a function of temperature, pressure, and mole fraction from a strictly foundational sense, but we know that for ideal gases, pressure, it's not a function of pressure, and when we see that this is equal to the pure species properties, right, that's not a function, that's not a function. So in reality, for ideal gas mixtures, it's really only a function of temperature. But for completeness, you'd want to think that the partial molar properties are always functions of temperature, pressure, and composition. But for ideal gases, that's not necessarily going to be the case. For the same thing holds true for the partial molar volume in an ideal gas mixture. That's just equal to the pure species volume as if it were an ideal gas. Same thing holds true for the enthalpy. Ideal gas mixture is equal to the pure species enthalpy, which is again only going to be a function of temperature. But for any real fluid, it's going to be different. It's going to be a function of more than just temperature. We also defined a concept. We defined the partial pressure. We typically denote it with a lowercase p. It's the mole fraction of the species times by the overall system pressure. That's a defined quantity. It doesn't really have a lot of physical significance because, as we mentioned with the Gibbs-Duhem equation, which is a consistency relationship that relates changes in partial molar properties, if I alter the composition of a real system, I can't say which of the new compounds is causing the pressure to go up or the pressure to go down. For an ideal gas, you can think of it that way. So if I have a mixture of A and B and I add more B to the system, well, I can say the pressure is going up because I'm adding more B to the system. But for a real true multi-component system, they all interact in slightly different complex ways. So strictly speaking, we can't attribute any increases in pressure to any particular species. Same thing as we can't particularly attribute any changes in volume or enthalpy to a particular species. It's all the mixture's fault. Now, the one area where I kind of rushed, and I felt that I was underselling the significance of the conclusion, was when we talked about entropy of mixing. So how we accomplished this derivation is we had a chamber filled with side A, a chamber filled with side B, and what we effectively did is we allowed A to expand into the volume of B, and we allowed B to expand into the chamber of A, and this is how we calculated the entropy of mixing. So the total entropy change of the system was how much entropy changed from A, how much changed from B, and from this we could figure out what the delta S of mixing was. So we found that the partial molar entropy of an ideal gas mixture is equal to the entropy of the pure species. In this case, let me write out the dependencies here. So this one actually is going to be a function of temperature, pressure, and composition, right? If I change the pressure, I change the entropy. This is going to be equal to the entropy of an ideal gas, which again is going to be a function of the temperature and pressure, plus this additional contribution, rather minus this additional contribution, so when I mix two fluids together, even if they're simple ideal gases, my entropy is always going to change. Now, if we look at this expression here, the natural log of the mole fraction. Now, the mole fraction has to be between 0 and 1. So 0, mole fraction, 1. What is the natural log of a number that is less than 1?
Negative.
It's negative. Right, a natural log function looks something like this if we have y and x. This is at x equals 1, y is 0. That is our natural log function. This is negative, that's a negative, this is positive. So the entropy of an ideal gas in a mixture is always greater than the pure ideal gas properties itself. Now we can also write then that the delta S of mixing, right? This is the same thing like we had on the exam, but we had delta H of mixing. The delta S of mixing for an ideal gas mixture, right? This term just goes away because that's subtracted out for the delta of the mixing. I'm messing this up. Now this term is also always going to be positive. Natural log of a number less than 1 is always going to be negative. This number is always going to be positive. That doesn't change anything. And the negative is always going to make it. So this term is always greater than 0. We always increase the entropy of the system by mixing it. That's effectively where we ran out of time before the exam. But through continuation of this, the Gibbs free energy is just simply a defined quantity. So if we substitute the relationships that we've already developed for internal energy, for enthalpy, for entropy, we can then derive expressions. I'll skip over the mathematics, but they're relatively straightforward. Just a simple substitution. The Gibbs free energy of species I while in an ideal gas mixture, again, is going to be a function of temperature, pressure, and composition because it contains this complicated entropy term. Is going to be equal to the Gibbs free energy of the pure species, again a function of temperature and pressure, plus, in this case, RT xi. So let's do the same analysis. Natural log of a number that is less than 1. This is always going to be negative, meaning that the Gibbs free energy, partial Gibbs free energy, is always going to be less than the pure species Gibbs free energy. Meaning that when I mix two things together, I'm actually going to be decreasing the Gibbs free energy. It's a lower state of free energy. So we have two ways that we've looked at phase equilibrium previously. One, we can maximize the entropy. In this case here, mixing two things always increases the entropy, no matter what, even in the most basic, simple systems of an ideal gas mixture. Second approach, if I mix two things, I lower the Gibbs free energy. Both of those tell us the same thing. Mixing is promoted. Fluids like to mix. And then we can show exactly the same thing for the Helmholtz energy, just to swap out the G's for A's, and we have exactly the same expression. So why is this significant? As we go off the rails, let's see if I can get this right. So when we look at the total Gibbs free energy of a system, G with an underbar, this tells us this is the total property of the mixture. We can write this as the summation of the partial molar properties, and this is basically just a definition. Right? This is how we defined more or less the partial molar properties so that it behaves this particular characteristic. We kind of skipped over the math, but to some extent that was one of the goals. So if we substitute in information here, we then have combine these two terms here, then I just get the total system enthalpy, and I leave these two terms lingering.
This is G.
What's that?
The H or G?
This one here? This one's H. So if I take the mole fraction times, so what I did is I substitute in the partial molar Gibbs for the partial molar enthalpy plus the partial molar entropy, which is our definition here. Well, let me sorry, I think you're a good point. So this is not, it's, let me see. Let me think about this. I'm borrowing from a bunch of different notations here. I'm trying to make sure I didn't make a mistake. Let's simplify this. I can get to the same point I'm trying to make without making sure I'm not screwing things up. There's nice big data table. There's nice big tables in the Sandler book that breaks down all the different ways we can write this out. So this is, so G over bar is defined. We can also write it as H over bar of I minus T. So if we do our substitution, I might have some lingering terms missing here. So that's fine, minus T times S over bar of I minus this is what I said, it's always dangerous when you make last minute changes. This would be the more appropriate way to write it here. the more complete way to write it. Yes?
Would that x of I, wouldn't that be inside the summation?
Yes, it would be. So this is a lot of work for me just to cross a couple things out, because what we're going to say is that, so this is an ideal gas for an ideal gas mixture. Ideal gas mixture. Oh, no, this is not working out right. I don't want it to be. This is going off the rails because I was sloppy with my math and my quick notes here. So what we'll say, okay, let's see. Here's what we'll do instead. Because I can't cancel this out saying that it's 0, the partial. Oh, here's one. Okay, this is why I'm messing things up. This is my problem right here. This is S under bar. That's why. That's where I was messing up. Because this extra R times the natural log, that makes the underbar turn into the overbar. That's what I was screwing up. Okay, now we're good. Okay, for simplicity, here we go. For an ideal gas mixture, the partial molar enthalpy is just equal to the pure species enthalpy. And for simplicity, we're going to say that's our reference state. So that means this term is going to go to 0. Sorry, I apologize for your scratchy notes. If we set the pure species entropy as equal to 0 also, then this term goes away as well. Makes our lives a little bit easier. So then our conclusion here is that the Gibbs free energy of the the total mixture is this function, summation of this function here. Okay. This is the goal we were trying to get to. So if we expand out the Gibbs free energy as a function of temperature, pressure, in this case we'll say it's a binary system, so a function of the mole fractions of components 1 and 2. Now these two are not independent functions, they're independent variables. They are dependent on one another, but just to make it clear. This is effectively the function we're going to be plotting. And we could, of course, substitute, x1 and x2 to make this a function of only one variable. So now let's take a look at this, because there's a lot of cool information contained within it. So we have a plot here of the Gibbs free energy on the y-axis, and then the composition on the x. All the way over here, we have pure component 2. All the way over here, we have pure component 1. Now, We are anchored at these 2 points based on our reference state that we assumed here, with the enthalpy and the entropy equal to 0 at these points, which makes it so we only are looking at what's changing effectively as a result of the mixing. So the delta G of mixing, this is the line that constitutes how much Gibbs free energy the pure species contribute. So if the line is above it, that means that it's a positive Gibbs of mixing. If the line is below it, that means it's a negative Gibbs of mixing, right? So if we plot this function out, we have a couple of issues here. So if I set if x1 is 0, if x1 is 0, which means that x2 is 1, let's see what we get here. This is a problem. The Gibbs free energy is RT times by 0. Natural log of 0 is negative infinity plus 1 times the natural log of 1, which is 0. All right, so we have all sorts of problems associated with this function. So we can play around and use L'Hopital's principle and actually figure out what the property value is as we take the limit as either x1 goes to 0 or x2 goes to 0. But we'll expand on that a bit more when we start talking about liquid-liquid equilibrium. But for now, I just want to draw out the function. What the Gibbs free energy function looks like is like this here. Now, the interesting characteristics is that the slope is negative infinity as it approaches. So what it looks like is that it approaches as a vertical straight line. So what that tells us is that when I start to dilute component 1 into a sea of component 2, I gain almost an infinite amount of entropy right from the onset. Because I'm mixing in and I'm giving a little bit of small component 1 a huge sea of component 2 to swim around in. So let's say, for example, hypothetically, that we no longer have an ideal gas mixture. So let me do this in blue so I can highlight it here. So let's say, for example, hypothetically, we have a scenario where the delta H of mixing is much, much, much greater than 0. Right now, this black line is effectively just the T delta S of mixing. Because in this way, how we drew this line and how we plotted this function up here, this is just the entropic contribution to the free energy. But let's say, for example, we have a large, large, large contribution. So this would be the case if I was mixing two things that really, really didn't want to be mixed, right? An oil and water system, for example. What would happen then is that if I plotted out the enthalpy of the combined system, it would look something like this. Two things will mix together if the free energy is lowered. Meaning that if I have a 50-50 mixture, I have my pure components here, the enthalpy and entropy are both 0 to start off with. So that means the Gibbs free energy of my mixture is always going to be on this line. So if the total free energy change is negative, they mix. If it's positive, they don't. Now the question is, what happens at these limiting endpoints here? Right? This function here has finite values for somewhere in the middle. And if we wanted to, we could crunch the numbers and plug in 0.5, 0.5, 0.5, 0.5. Right? It's going to be a negative number, but it's a finite negative number. And of course, some things don't mix. So if I put a 50-50 mixture together of any two random fluids, odds are they're not going to mix particularly well, and you'll have phase separation at that conditions. That's because the enthalpy of the mixing is significantly more positive than the entropy of mixing at that same set of conditions. But if we zoom in here, No matter how much two fluids hate each other, they will always have exactly the same shape. So if I zoom in here, now I'll say this is x1 here is equal to 10 to the minus 6, for example. Very, 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 very small mole fraction. Even in the case of something horrendously unhappy. We're always going to have a super large negative component that approaches with an infinite slope, and we're going to have an enthalpic component that approaches with a finite slope. This one here is always going to be infinite slope. How do I know it always has to be a finite slope? Well, law of conservation of energy dictates that it has to be. So if we view the system as a collection of atoms, one way that you can approximate the total energy of the system is one, of course, what we do for the ideal gases. You have ideal gases vibrating around, wiggling around, and all that kind of stuff. But you also have a contribution from the interactions between the particles. That's what the A term corresponds to in the van der Waals equation. So what happens is when I insert, if I have a sea of particles of one type, and I insert in a particle of a different type, I add up the interaction energy between all of these different particles, and that gives me an indication of how much the energy changes when I mix these two fluids together. Right, this approximation here is called pairwise activity. It's more or less what all thermodynamic calculations are based on. It's not accurate, but it's the best we can do. If this procedure, this is exactly what I'm doing, right? I'm taking one molecule of component 1 and I'm shoving it into a sea of component 2. If this interaction energy is infinite, then it would counteract the negative infinity of the entropy. So meaning that no matter what happens, I need a different color here, the Gibbs free energy is always going to be a little bit of a down and then a back up. There's always a little bit of a Gibbs free energy minimum for any fluid mixtures, no matter what. So this tells us that every component is at least partially miscible in every other component. And the analogy I like to use is, let's say I had a glass of water. You say, okay, oil and water don't mix. But then let's say I take some crude oil or some used engine oil, whatever the case is, and I pour it on top of that glass of water, then I shake it up. The phases separate, and say, okay, well, do you want to drink that water? I think everyone would say no. Hopefully everyone would say no. Because we know that a little bit of those petroleum products, those organic products, are always going to dissolve in the water. And a little bit of that water is always going to dissolve in the oil. The rationale for why this occurs is because of the entropy of mixing that we get even for the simplest of ideal gas states. So everything is always miscible in everything else, at least just a little bit. Always. And it's because of the shape of the entropy curve. And that's why in your handout sheet there, we'll talk about in a second here how we define the partial molar Gibbs, and rather we define the fugacity. We're defining the fugacity to avoid this complication here. And this is the whole reason why we defined fugacity in the first place. Why we did it for a single component system was just sort of for fun, more or less. It wasn't necessary. But when we talk about a multi-component system, this discontinuity here is captured in all of the ideal gas properties. So instead of us worrying about the discontinuity in all of our calculations, we're just going to factor it out. And that's why our partial fugacity is going to be defined as the deviation from ideal gas mixing to real fluid mixing. So that's why I felt a little bit, we shortchanged a little bit before the exam talking about entropy. Okay, any questions on this concept here? Messed up the math a little bit, but I think I recovered at the end. I think I got it captured well. Any questions? The most important thing to walk away from it is the concept, though, and the rationale of why we bother defining the fugacity in the first place. And this is the whole rationale behind defining the fugacity. So with the last little bit of class, about 15 minutes or so, I'm going to run through a few more concepts. Let me see if I can get out that same. I handed out all the equation sheets. Get one in front of me so I can take a look at it and refer to it. So these equations, there's a lot of different ways to write all of these things when it comes to mixtures, and so I like to have the summary equations so you don't have to worry about scrambling them down too much. All right, so if we expand Gibbs, this again is the starting point for virtually everything that we like to do. Right, we're going to expand the Gibbs free energy, take the total derivative with respect to changes in temperature, pressure, and composition of the number of moles of each of the individual species. And this is a similar approach that we took to defining partial molar properties. We're looking at changes in temperature and pressure. This can be related to the combined first and second law. And we can establish thermodynamic identities. So this is very similar to what we did at the start of the class. You also had a homework problem on effectively doing exactly the same thing, deriving identities for open systems. So following a very similar procedure to what we did for deriving Maxwell relations, we're going to swap the order of derivatives. So we know that the partial molar entropy can be written as, right, this is effectively just the definition, mixing at constant temperature, pressure, and holding Nj not equal to Ni. Or sorry, yeah, J not equal to I. Now this is equal to, I'm going to drop the little subscripts over here to make it a little bit easier to read. This is just the thermodynamic identity. Then we can swap the order. Right, swap out the order that we take the derivatives. This is again, this is the partial molar property. And we come up with another identity, but this case for a mixture. So more or less, what we're showing is that with the formulation of how we write partial molar properties, all of the identities that we have in existence, you can just put an overbar on top of it and it's still a good identity. Same thing for the partial molar volume. In this case, I have an NJ written here because we're using subscript I to define this particular species, so we're holding all the other species constant. And we're basically only a few steps away from defining the partial molar fugacity, or the partial fugacity. It's not really a molar property. So we follow along a path of constant temperature, same approach we took for defining fugacity. We want to calculate the Gibbs free energy change going from state 1 to state 2. This is temperature 1, pressure 2, minus the partial Gibbs of temperature 1. Let's write temperature. I want to write temperature 1. P1 and composition. I will say at constant composition. Right, so what we're doing is we're effectively just taking our total differential, holding temperature constant, this term goes away, holding composition constant, this term goes away. We're not mixing any new species in, we're not changing the temperature. This expression here is effectively VDP, but we're doing it for a multi-component mixture for the partial Gibbs, meaning that we can take all of our expressions, just draw a line on top of them, and it still works out just fine. And that's what we're doing here basically, is we're just integrating this expression. And from here, we define our fugacity. As such, natural log So, the concept here, this is our definition of the partial fugacity. Once again, the idea is that we're pretty good at ideal gas calculations. So when we define the real fugacity, what we were looking at was the volume of the real material minus the volume that it was as an ideal gas, and then we integrate that change until we come up with whatever the final temperature and pressure conditions are, and that was our definition. So if you recall back on the fugacity calculations, we would substitute in, we actually didn't really use this equation too much, we transformed it a little bit, and if you look at, let's see, the equation sheet, I've got a last one here on the bottom. We have fugacity from an equation of state. This one's been transformed in terms of dV as opposed to dP. So it's a bit more complicated to substitute in an equation of state and do the transition, but in general, what we're doing is we're looking at the deviation in ideal gas behavior, taking it to real system conditions. Then it just so happens to work out that based on how we've defined the fugacity, that we can still use it in place of the partial molar Gibbs in terms of our phase equilibrium calculations. But we recall what we did here is we took the ideal gas law, substituted in for this expression. We took our real equation of state, substituted in for the real property conditions. In fact, you could numerically integrate this if you so were inclined, if you had access to either PV data or something like that. You could numerically determine what the fugacity was. But it's almost the same definition, except we just draw little bars on top, as opposed to bars on the bottom. That is our definition. But we have a long, long list of different ways we can write this expression out that may be useful in different circumstances under different instances. And I may update this handout under different circumstances if there's some other expressions that are useful. But I don't want to have to just write out a bunch of things. So the idea here is that what we're effectively doing, I'm going to say this is pressure what we're effectively doing in the partial molar fugacity, or rather partial fugacity approach, is what I want to know is I want to know up here at some x1 value, at some pressure, at some temperature, what is the partial fugacity, and then likewise we can also think of that as what is the partial molar Gibbs free energy. So the approach that we're taking in order to calculate the fugacity is we first mix the two components together. In this case, this would give us the fugacity of an ideal gas mixture, which is related to the Gibbs of an ideal gas mixture. Then we take that entire system and we pressurize it. dt is equal to 0, dx is equal to 0. And we're only changing the pressure. So the fugacity, this term here, is that leg of the journey that takes us from mixing two fluids together as an ideal gas and then pressurizing it up to actually solve real problems. This is not a trivial process. And for the most part, we have to rely on empiricism. So if you take a look at the last equation here, it says fugacity from an equation of state. It's a big, long, complicated equation, where we have the natural log of the partial fugacity coefficient RT over V minus that's a sloppy reproduction of the equation. This term here is effectively just our ideal gas pressure. Now normally, in our normal fugacity, this is just the pressure which we would get from an equation of state, this term. But in a multi-component system, it's not as simple as just varying the pressure. We now have to evaluate this very unpleasant derivative. What this is saying is that how does the system pressure change in a multi-component mixture as a result of adding a little bit of species 1 or I into the system, or subtracting a little bit of species I from the system? Now, if we look at the van der Waals equation of state, there is nowhere in this equation where I can insert the number of moles of each individual species. So instead, it all breaks down and we all resort to empiricism. So the strategy that most people take is to assume a one fluid model, meaning that you calculate pseudo properties of the A and B coefficients, and that you relate this and turn it into RT V minus B of the mixture minus A mixture over B squared. Then in these expressions, we have to have a way to calculate the coefficient A of a mixture and the coefficient B of a mixture in order to evaluate this derivative. So the whole system becomes extremely unpleasant. Not to say it can't be done, and it hasn't been done. Of course, it's all been done. But it gets really sloppy. So instead, what we tend to do, for gases, this approach really works reasonably well, unless it's some really crazy, binding gas that dimerizes or trimerizes in the ideal in the gas state. But for any liquid, right, we were barely able to predict liquid properties even for pure components. Right, the van der Waals equation, as we saw, was dreadfully terrible for the ammonia system that we were tinkering around with. Payne-Robinson, not too bad, but ammonia is a very simple liquid. When we start to get to much more complex systems, even water, we cannot predict liquid properties well at all. So it is a dream and a hope that we could calculate the mixture excluded volume, which is actually not that bad, but the mixture interactions, evaluate this integral, and then somehow hope to very accurately predict all the phase behavior. So instead, we rely on empirical terms like the activity coefficient. So we'll be talking about that, I think, on Wednesday, but the activity coefficient is a way that we can kind of short circuit this whole tedious equation of state approach to calculate phase behavior, and instead rely on categorizing different types of interactions. So a lot of the most accurate phase behavior models are not based strictly on a single pure equation of state. It's based on empirical fitting of similar mixtures and then trying to draw conclusions about those other measurements. And this is where a lot of the elegance of thermodynamics starts to break down. But ultimately, the goal here is that we're trying to get to the answer. So the elegance of how we got to here is going to formulate the system that we then use to tabulate real experimental measurements of actual phase behavior in real systems. And so when it comes to vapor-liquid equilibrium, and especially liquid-liquid equilibrium, we have to rely on empirical measurements. We cannot fully predict everything from the bottom up. It gets too complicated, unfortunately. Any questions? All right, see you Wednesday.